Conservation of energy is one of the most important laws in physics. It's one of the most important laws in nature. It basically covers everything. And when we look at conservation of energy, we're actually seeing a symmetry, which is something that follows Noether's theorem. And Emmy Noether was a famous mathematician who recognized anytime we have a symmetry in nature, that results in a conserved quantity. And the symmetry that we have here is when we look at energy, especially later works that we don't cover in this chapter by Lagrange and Hamilton, if we do a transformation in time, we see that the equations don't change. And of course, this results in a conserved quantity, in this case, energy. Other conserved quantities, such as conservations and transformations in space, result in conservation of momentum, which we'll get into in the next chapter. But again, conservation of energy is so important. When we say a physical quantity is conserved, we say that its value doesn't change if we have a closed system. We don't introduce energy from the outside. We don't allow the energy to go to the outside. Basically, these isolated systems will only interact through conservative forces and keep the total mechanical energy of the system constant. Now, there are cases where we don't have mechanical energy conserved, but when mechanical energy is conserved, we say that the mechanical energy at the beginning of any interaction is going to be equal to the mechanical energy after the interaction. Essentially, the only two forms of energy that we'll deal with here are kinetic energy and potential energy. And whatever the kinetic energy plus the potential energy is at the beginning will be the same at the end. Now, of course, we have systems where mechanical energy can be transformed to other forms, or vice versa. We can have other forms of energy transformed into mechanical energy. Here, although energy is conserved, we have to conserve energy. The mechanical energy, because it's being transformed, is not conserved. Here, we write the equation for our work energy theorem as the non-conservative work, we put that on the left side of the equation, is going to be equal to the change in mechanical energy. That is the change in kinetic energy plus the change in potential energy. We can write this a number of different ways. We can write it as the work done by non-conservative force is equal to K final minus K initial plus U final minus U initial. We can change it up a little bit and say that the non-conservative work is equal to the mechanical energy at the beginning of the interaction minus the mechanical energy at the end of the interaction. Basically, my non-conservative work represents what I'm changing in terms of the total mechanical energy of the system. If it's friction, I'm taking energy away from the system. If it's, say, an electrical motor, I'm converting electrical energy into mechanical energy, adding mechanical energy to the system. Even my own influence, if I use my muscles in my hand to push on something, that's adding mechanical energy to the system. So what are we going to do? In this part, we're going to look at, first of all, mechanical energy being conserved, where then the non-conservative work is zero, so there's no change in kinetic energy plus potential energy. Those two can change as long as the other one is changing. And then we're going to add frictional forces, just to give you an idea how a non-conservative work would operate. So basically, when we're looking at these different systems, we are going to look at, if it's a non-conservative work being done here by non-conservative force, we're going to see how the force is applied. Obviously, we know that work is equal to the integral of force dot dr. So in the case of friction, heat will be generated as work is done on whatever is experiencing the friction and taking that mechanical energy away and converting that into heat. There's even sound generated during a collision. This is acoustic energy, which must be considered and taken away from the system. In collisions, we'll see that there's no such thing as a perfectly elastic collision on a macroscopic scale because we're always losing some energy due to the collision. And as we said, motors can convert electrical energy into mechanical energy. Generators can convert mechanical energy into electrical energy, and they can change the overall amount of mechanical energy that we have from beginning to end. Let's start by analyzing a very simple system. I'm going to look at a pendulum, and a pendulum, we're going to say is a magical pendulum. There's no, friction here. There's no viscosity due to the air. Basically, it's going to be able to swing back and forth forever. It's sort of a perpetual motion machine. And essentially, when we're looking at this, we have to consider what the position of the mass is at the beginning of whatever, change we're looking at and what it is at the end. So pendulum's very simple. Galileo understood that pendulums had constant period at which they'd swing back and forth. And we know that at the highest point, its potential energy is going to be the greatest. As it swings down, that potential energy is converted into kinetic energy. At the bottom, it has its maximum kinetic energy. There's no potential energy left in the system, and then it swings back upward. So looking at this, we can see a lot of similarities between something in free fall, but the main difference here is we have one conservative force, and that, of course, is gravity, which is going to act on the mass. And then we have a restrictive force that doesn't do any work, and that's going to be the tension from the string. So again, we start out with some initial potential energy, mgh. H represents the height at which the pendulum is above its lowest point. This diagram's a little bit off because my center of mass is probably somewhere here, and that center of mass only changes by this much, but let's pretend that the center of mass drops by some distance of h. So we're going to go from potential energy of mgh to a potential energy of 0. We start at rest at the top, so my kinetic energy is 0, and that kinetic energy becomes 1/2 mv squared. So in analyzing this, I can look at my conservation of mechanical energy. Again, there's no non-conservative forces that are present here. My kinetic energy initially is 0, so I'm going to just eliminate that term. My initial potential energy is mgh, so that's going to go in right here. My final energy, kinetic energy, is going to be when the pendulum is down here, 1/2 mv squared, and I'm going to make my final potential energy to be 0 at the bottom there. In fact, that was important for defining the initial energy because this height was a potential energy compared to the lowest potential energy could have when it was at the bottom of the swing. So very, very simple problem here. My initial potential energy, that's all my mechanical energy at the beginning, equals my final kinetic energy, all my mechanical energy at the end. I get mgh equals 1/2 mv squared. The masses cancel out. I solve for v squared here. V squared is equal to 2gh. And finally, I can find my final velocity. At the bottom, the velocity is going to be the square root of 2gh. And if it swings upward, because mechanical energy is conserved, it will reach the same height at which it started, and the kinetic energy will drop down to 0 there. Now, what's interesting here is this is the exact same result as if I dropped a mass an equivalent amount of height. Now, what's different here is my conservation of energy equations don't give me velocity. What they're really doing is they're giving me speed, because the kinetic energy, we square the speed here. Even if that were velocity, I would be only considering the magnitude here. In my kinematic equations for falling body, I have v squared equals v0 squared minus 2gh. Here, y is equal to negative h. So v squared is going to be equal to negative 2gy. Again, y is negative h. And I solve for v, I get the square root of 2gh here. That's for a falling body. We've seen this type of problem before. What's interesting here is I'm only asking, what is the final speed? Whether I drop the pendulum bob, just without a string, or I restrict the motion of the pendulum bob to swing such that the velocity is vertical, I get the same result because these are conserved quantities, okay? Basically, the energy, whether it's the energy of a falling body, going downward, or the energy of a pendulum swinging off to the right or positive x direction here, I'm going to have the same kinetic energy at the end of the process. And again, if I look at the total energy in my system, I can see how the potential energy is dropping, dropping, dropping until I get to the bottom of the swing. The kinetic energy is rising, but the total mechanical energy never changes. Okay, so again, we saw how we approach these problems. We're going to define our system. We're going to verify that there are only conservative forces present. What are the forces present? We had gravity. Therefore, we could assign a potential energy to that. And the other force was from tension, which was always perpendicular to the motion. So it never could do any non-conservative work on the pendulum mass. Select the location of zero gravitational potential energy, where y is zero, okay? We did that. We said that when it was at the bottom of the swing, that's the least amount of potential energy that the system could have due to the restriction of the string. And therefore, that's where I said y is equal to zero there. And that's where I said that is going to be my potential energy of zero. Identify 2 points of interest. My starting point and my finishing point were at the top and the bottom of this. The other point should be where you want to find something. What was the other point? At the bottom of the swing, I was finding out my speed. Okay, apply conservation of energy equation to the system. That was simple. I had my initial mechanical energy is equal to my final mechanical energy. And then again, typically a speed associated with kinetic energy, that's what I was looking for, or a position associated with potential energy is what I'm looking for. Now, again, I could do this problem backward. I could say that this pendulum bob has some initial kinetic energy, and I want to find out how high it goes. If I work backwards on this, I could have started with some initial velocity, plug that into my 1/2 mv squared, and then found out the final height, basically just reverse engineering what I did the first time. So again, that's a very important point. We're limited here. The advantage of conservation of energy is we're dealing with scalars. So we don't have to worry about, vectors in this case. For instance, the tension, if I'm looking at the force here, would create a force that's in a direction that's not aligned with the vertical direction where weight is going. It'd be a very complicated system to analyze just in terms of forces and determine the acceleration at any point and find the final velocity here. Here, if I can analyze the motion with the diagrams, even though the equations don't give me the direction that it's going to go, understanding the restrictive force of the tension, I know how it's going to behave. So more powerful because it's a simpler type of system to solve. Less powerful in terms of you have to use your intuition to understand where the velocity is pointing. Now, again, we're going to see almost the exact same situation. We're going to say that we have a falling body here. We can use a kinematic equation for a free-falling object. V squared equals V0 squared minus 2GY to get the same result. However, here, we're going to use conservation of energy and just prove to ourselves that we get exactly what we expect. We have a diver who's going to start at 10 meters. They're going to drop to 5 meters, and I want to find out how fast they're going at that particular point. We're then going to see this falling body again go all the way down to 0. And we are doing the idealized case where we're not considering air resistance. So both this equation and conservation of mechanical energy work here. So again, find the speed halfway. We want to find the speed from 10 meters to 5 meters. Here, the initial kinetic energy, we're going to say is 0, so that's going to drop out. The initial potential energy is mgy, that's going to be 10 meters above here. And here, I'm not going to fall all the way down to the surface. I'm falling down to 5 meters down. So I will have a final potential energy, but I want to find out my final kinetic energy here. So once again, I get this equation right here. M can be divided from both sides. I get this relationship. GYI is equal to 1/2 VF squared plus GYF. And this, in fact, again, is the same result I would have had if I used this equation right here. We can recognize this. Y here is really this distance here, okay? This distance here is going to be 5 meters. We've done this a little bit differently, where we started at 10 meters and dropped to 5 meters. We still get a difference here of 5 meters, and our result is that our final velocity is going to be 9.9 meters per second squared. Exactly what I get with the kinematic equations. If I go a full 10 meters down, same thing. The only difference here is my initial kinetic energy is 0, and I've defined my potential energy to be 0 at the bottom. Now I've got a distance of 10 meters, so my final velocity is 10 meters per second. Now, you may ask, well, I've fallen 5 more meters. Shouldn't I be falling with a velocity twice as much as when I was at 5 meters? The answer is no. Think about this. My acceleration is constant all the way down, but it takes me a longer time to go from here to here than it does from 5 meters to 0. Here I'm starting from 0, and I reach 9.9 meters per second. At here, I'm 9 meters per second, and I'm traveling faster, so I have less time to accelerate, so my change in velocity is only 4 meters per second from 5 meters to 0, where it was 10 meters per second, roughly 10 meters per second from 10 to 5. So conservation of energy, conservation mechanical energy, and the kinematic equations give me the same result. So I'm happy with this. What we learned previously works here too. Here's where it's not so easy to use kinematic equations, because if I look at a roller coaster, I know with the roller coaster, the slope of the tracks are going to determine my acceleration. So can I use my kinematic equations of motion? No, I can't. Because if my acceleration is not constant, my kinematic equations don't work. Here I have an acceleration in the direction of the track. Here I have an acceleration in the opposite direction of the track, where I'm slowing down, speeding up, slowing down. And analyzing the forces here would be quite challenging. I'd have to have some mathematical form for this curve of the track. So Newton's laws aren't going to do me very good here. However, conservation of energy makes this actually a very simple problem. I can ask, what is my kinetic energy and my potential energy at the beginning? What is my kinetic energy and potential energy at the end? And solve for my unknown, which would be, in this case, I'm trying to find out how fast I'm going here. Now, again, this is an idealized system. There's no frictional force here to do work against the roller coaster. So I can just use conservation of mechanical energy, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Okay. Oh, by the way, I have defined this point right here as having 0 potential energy. So even though it drops down 25 meters from its initial height, 20 meters, that's where y is going to be set to be equal to 0. And at the top of here, y will be equal to 20 meters. So again, I'm going to start with my roller coaster not moving. So there's no kinetic energy at the beginning. I'm going to end up with no potential energy at the end when I've dropped down 20 meters. And I have the same problem that I had with the pendulum. Potential energy initial equals kinetic energy final. All the energy's worried about is, what is my initial height? What is my final height? Because that's the only thing that influences my potential energy. My kinetic energy, I start with none. How much do I have at the end? Same equation I had before. V equals the square root of 2gh. So in this case, I can find my final velocity, 2 times roughly 10 times 20 is going to give me 400. So that's 400 meters squared per second squared. I take the square root of that. The square root of 400 is 20 meters per second. Okay, I've solved the problem. Now, let me change this a little bit. Let me give it some initial velocity because that's more realistic. I'm going to come over this hill and, I'm not going to, come exactly to rest because I always have that problem if I've designed this the wrong way that the roller coaster is going to go backwards if I don't have exactly that amount of energy. So we're going to say now we're going to start with initially 10 meters per second. Not all that much more complicated. Notice I just preserved this extra term, my initial kinetic energy. So my initial kinetic energy plus my initial potential energy is going to equal my final kinetic energy. All the mechanical energy is preserved. This is what the equations look like. I have kinetic energy initial plus potential energy initial equals kinetic energy final. Divide both sides by mass. Mass drops out of the equation. And that's usually the case when we have conservation mechanical energy. We can drop the mass out of the equation. V final squared equals 2gh plus V initial squared. This, again, is actually the same equation that I would use if the roller coaster were just dropping, free falling 20 meters. That's not a pleasant thought to think about. But my final velocity, my final speed, I should say, is equal to the square root of twice the gravitational acceleration times the height. That was what I had before, but now I have this extra term V initial squared, which came from my initial velocity. So when I plug this in, I get the same term I had before. This is 400 plus 10 squared is another 100. I'll get 500 meters squared per second squared. The square root of that is 22 meters per second. So the faster I start out, the faster I'm going to end up because I have to conserve that energy. Okay, let's see if I can do an even more realistic situation. Let's now deal with friction. And in this case, of course, I have a non-conservative force, which means that the mechanical energy I have at the top of the hill is going to be more than the mechanical energy I have at the end because the frictional force is going to rob me of some of that mechanical energy. Now, my friction is 100 newtons, and that's going to oppose motion, okay? Oppose motion, okay? So I'm going to say my frictional force is 100 newtons. That's probably not completely realistic because my frictional force will depend on the normal force, which will be less as I'm going downhill. But we'll use this approximation here. My total length of the track from here to here is going to be 120 meters. So in calculating the non-conservative work, okay, which is going to go on the left-hand side of the equation, that's going to be basically negative 100 newtons times 120 meters, okay? We're still going to have a change in kinetic energy. We're going to still have a change in potential energy. But really, remember, I'm trying to find out my final speed here. And in that particular case, I'm going to solve my change in kinetic energy last. I'm going to calculate this first. I'm going to calculate the second. Then, because this is unknown, I'll calculate that based on this and this. Okay, watch how I do this. So what is my work done on the roller coaster? Again, it's friction, so it's going to be negative. Negative 100 newtons times 120 Newton meters is negative 12,000 joules. Okay, so that is going to go on this side of the equation. Now I'm going to do my change in potential energy. Same thing. Okay, I start out with potential energy of mgy. I end up with a potential energy of 0. So 0 minus, there should be a negative sign here. Sorry about that. There should be a negative sign here. Oh, no. I guess y is negative 20. That's fine. Okay, y is negative 20. So my final potential energy is 0. I've chosen y to be 0 at that height. I subtract off my initial energy, 500 kilograms times 9.8 meters per second squared times 20 meters. Notice I have to include my mass here. My mass doesn't drop out of the equation. So I had to know how massive the the roller coaster was in this problem, because that mass associated with the energy, I've got to put energy to energy. My work has to be matched with the potential energy. So I can't just divide mass out, because mass isn't part of the non-conservative work here. So I lose 98,000 joules of energy as I go downhill, okay? And that, most of it's going to be converted into kinetic energy, but some of that is going to be converted into heat due to the non-conservative work done by friction. Okay, so I have my work, I have my change in potential energy. Now I can solve for my change in kinetic energy. So rearranging this equation, delta K is going to be equal to my work non-conservative minus my potential energy, my change in potential energy. So that becomes this equation. This value is negative. I subtract off by a negative value. I get positive here. And I can see, well, most of the potential energy was converted into kinetic energy. I have 86,000 joules of kinetic energy at the end of the problem. Okay? I should say it's not at the end. That's my change. I did have some energy at the beginning. I'm going to have even more at the end. But again, I like to solve these problems as I calculate the work, I calculate the change in kinetic energy, I calculate the change in potential energy. If I know those, or I have the information that I need to find those, and one of these is going to be unknown. It might be work. Here it was the change in kinetic energy I didn't know. It might be the change in potential energy. Okay, so at the very end, here's my equation for change in kinetic energy. My change in kinetic energy is going to be my final kinetic energy minus my initial kinetic energy, or I can say my final kinetic energy is whatever my initial kinetic energy is, plus what change has taken place, okay? So initially, I've got to calculate what was my kinetic energy at the very beginning. It's 1/2 500 kilograms times 10 meters per second squared. So that is going to be 25,000 joules, okay? Plus I gain 86,000 joules, and my final kinetic energy is 111,000 joules. I can then use that to find the final velocity, final speed, but I know it's going in the positive x direction. So kf equals 1/2 mv squared final. V final is equal to the square root of twice the kinetic energy final divided by the mass. I get 21 meters per second. Okay, so you see how this problem has evolved. We did the case where we're starting at rest. We got 20 meters per second as a final velocity. Then we said, well, that's not realistic. We probably would have some initial velocity at the top of the hill. We ended up with 22 meters per second. And by considering friction, I only lost 1 meter per second in terms of the overall velocity. So that is my roller coaster problem. And again, we couldn't have done this very easily using forces. Again, you talk about the complications of having to know, what the forces at any point. It probably involve, a lot of, crazy integration to find out what my final quantities were. But again, using conservation of energy, it makes what can be a very complex problem much simpler. Now, we haven't covered any elastic potential energy, but we can pretty much treat those problems the same way. The elastic potential energy is equal to 1/2 kx squared. And if we have some system where we do have this energy involved, we would simply treat this. And by the way, I've got to apologize. Our textbook uses U for potential energy and K for kinetic energy. There's some switching back and forth with some of these diagrams that I've borrowed. But for instance, for potential energy, we would just put it on the right-hand side of the equation for spring potential energy, just like we did for gravitational potential energy. So here I can say I have non-conservative work pushing into the block, adding energy into the system. That becomes spring potential energy, 1/2 kx squared. And then when the spring is released, that's going to launch this mass. If we consider this to be a frictionless plane, and the final kinetic energy is going to be 1/2 mv squared. If I want to solve for that problem, we again would consider the non-conservative work that my hand did, adding energy into the system. So that would be positive here. What was my change in kinetic energy from beginning to end? What is my change in gravitational potential energy? There is none. And then finally, what is a change in potential energy? Now, in this system, I've got to be careful because where was my starting point? When I loaded the spring, okay, was that my starting point? When I did work on this, did I start it from when the spring was compressed? I have to be careful there because there are two different starting points and then a different final point for when the mass was released. And again, if there's no non-conservative forces acting on this, we could just say the total mechanical energy at the beginning is equal to the total mechanical energy at the end. Kinetic plus potential energy from gravity, potential energy from the spring, same problem-solving strategies apply, okay? We're normally looking for a final position or we're looking for a final velocity, all right? Like for instance, if I hang a spring on a mass, it has maximum gravitational potential energy at the top. It has maximum kinetic energy at the middle of the fall. And then at the bottom, the spring potential energy is maximum. And we can calculate the velocity, the maximum velocity, based on our different energies here. Okay. Here, by the way, we would probably define my gravitational potential energy as being 0 at this point in order to say, what my gravitational potential. This is a little bit tricky because just where we're introducing our different potential energies. So again, non-conservative forces, if we have friction, we saw with the roller coaster that friction is always always has negative work done. That's going to take energy out of the total system. Let's look at a more complicated system when we had combined motion. This was the half-Atwood's machine. And we did this with Newton's law, and we came up with, pretty good results for this. But for instance, we can solve this using conservation of energy also, but we have to consider the mechanical energy of mass 1 at the beginning, the mechanical energy of mass 1 at the end, the mechanical energy of mass 2 at the beginning, the mechanical energy of mass 2 at the end. So here, we have work being done by friction, and we're going to say that block M1 moves some distance, okay, which is going to be the same as the movement of block M2. Block M2 is going to change its height by delta y, so that's going to be the same distance that we slide the block M1 across the table, okay? Friction is equal to mu M1 times g. We're on a level surface. Therefore, the work done by the non-conservative force is friction times the change in distance. We have a constant force, so we can do that. We don't have to integrate. So we get negative mu m1g times delta y is the work done by friction. Okay, now m1's not going to change its height, so there's no change in potential energy up here. It's just going to start from rest. It's going to accelerate and have some final kinetic energy after it's moved some distance delta y. M2 is going to have initial potential energy, and that potential energy is going to decrease, but it's also going to gain kinetic energy. It's going to be in motion at the end of the problem. So here, I want to find out what is my final speed after I've moved some distance. All right. I can reverse that and say, how far does it need to go to get some final velocity, 2 meters per second? But here I'm going to find my final velocity. That's going to be my unknown here. So again, I'm going to find non-conservative work. Trying to find my change in kinetic energy. That's my unknown, just like with the roller coaster. My change in potential energy is only going to be due to mass 2 changing its elevation. So here's my non-conservative work. I find that. I need to find my non-conservative potential energy. That's just m2g delta y. Okay. I've made a little bit of a mistake here. Okay. This should be absolute value of distance that it moves. So we're still going to get a negative value here. I'm going to have to be careful of how I plug this in. Delta y here is technically negative. So I've got to be careful with the way that I write this out. You know, I guess a better way to do this would have been to use h here, which is the height that m2 drops, and use h here with a negative sign here. So again, my bad on not being consistent here. But again, the change in kinetic energy, I consider kinetic energy of mass 1 and mass 2. What is final minus initial? This can be written in more compact form. Obviously, these terms go away because I start at rest. Or I can just write it as 1/2 m1 plus m2 in parentheses times v final squared because they're both moving at the same velocity. Okay, plug them all in. I'll put this one here. I'll put this one here. I'll put this one here. Again, being careful with my negative sign. Okay, here we go. So this here's with my negative sign. My change in potential energy, again, this would be, this would be negative. But, that's some of the problem that we run into when we're using connected bodies. We have to make sure that we're connecting the motion of one with the motion of the other. And you can see here, in the end, I did a little sleight of hand here when I combine the two. Here you can see that my final velocity squared depends on how far I go. Obviously, the more massive M2 is, that's going to put more energy into the system. The more friction M1 has, the more energy that's going to remove from the system. Now, I say put into the system, create more kinetic energy. Then obviously, we have the total masses down here because the system does have inertia. So my final velocity looks like this. And again, that's the same exact result I would get if I calculated the acceleration from Newton's laws of motion. And then I used Vf squared equals V initial squared plus 2 times the acceleration of the system times the motion moved. So this saves me that step because again, going back to what we did with Newton's laws, we had to find acceleration first and then use the kinematic equations of motion to find the velocity last. Here, the velocity just falls out of the whole thing through conservation of energy. Okay. Sometimes we can't avoid using Newton's laws. Sometimes we have to actually combine a Newton's law type problem with the conservation of energy problem. And loops in a roller coaster are a really good example of where we're going to merge those two worlds. Now, in this case, because we're going around in a circle, we're going to have to consider centripetal force here. So we're going to combine what we know from centripetal force with conservation of energy. Okay. In the loop, we are going to eliminate friction because we just don't want to deal with an added complexity here. And we're going to look at our energy at the top of the loop, okay, and how fast we need to be going there to balance out weight with the centripetal force, how fast we're going at the bottom of the loop. and how much centripetal force we need there, okay? So our potential energy converted to kinetic energy, and we're going to calculate the centripetal force at the top and the centripetal force at the bottom. Okay, first of all, notice the shape of these loops. They're teardrop shape, and the problem that we're going to analyze is a roller coaster going in a perfectly circular loop. Now, the question is, what speed must the car have so it will just make it over the top of the loop without any force on the rails? Okay, what does that mean? That means that typically these rails create a normal force. Now, because the rails hold the roller coaster onto the track, that normal force can point to the center of the centripetal force, or they can point downward. So for instance, if gravity were not a thing, or I should say, if gravity were really intense compared to the amount of added centripetal force I get from this, the normal force would actually have to hold the roller coaster up so it didn't fall. So if I was going too slow here and just had enough energy to make it over the loop, the rails would be holding the roller coaster up. I want the condition that the rails don't apply any force at the top here. That really gravity is providing all the centripetal force I need to make it around that circular loop. Okay, so what speed must I have so that it will just make it over the top of the loop without any force from the rails? No normal force, only weight. B, after it completes the loop, what will the speed be at the bottom of the loop? Okay, and finally, what is the normal force at the bottom of the loop? And that will tell us why this shape doesn't really work for a roller coaster. So at the top of the loop, remember, we need a force. We're going around in a curved path, okay? But we want the curved path to just be due to weight, okay? Sort of like the moon. The moon goes around the Earth. Why? Because the Earth is pulling it down to the center of the Earth. Here, why do we make it over this loop here? Because the weight of the car is providing us with our centripetal force. There's no other force acting on here because the rails don't provide any force. So the condition is the sum of our forces is going to be equal to the mass times the acceleration. Here it's all centripetal acceleration. That's equal to mv squared r. So here's my total force. Well, my only force is weight, mg. So this equals this. The masses cancel out. V squared over r is equal to g. Well, this is really easy. And v squared is equal to rg. So v is just r times g. Okay. How fast do I need to go so I feel weightless at the top of the loop? There's no force from the rail, so I don't feel anything. I'm in free fall, essentially. I need to be going 9.9 meters per second. Easy enough, okay? Now, notice that the radius of curvature is 10 meters, but at the top of the track, I'm 20 meters above the bottom of the rails. Now, this was going back to our Newton's laws chapters. Now we're going to go back and return to our conservation of energy chapter. At the top of the track, I have more potential energy than at the bottom of the track. How much potential energy is converted to kinetic energy as I go to the bottom? Well, here's my conservation mechanical energy equation. Again, no non-conservative forces, so I don't have to do the W NC equals change in kinetic energy plus change in potential energy. My kinetic energy at the top is going to be based on that nearly 10 meters per second. My potential energy at the top is due to 20 meters up. Remember, the radius is 10 meters, so the diameter is 20 meters. I don't know my kinetic energy at the bottom and my potential energy at the bottom. I'm just going to call y final equal to 0, so that term drops out. So I get this equation here. Again, I see a very familiar equation, okay? Looks like my kinetic energy, kinematic equations, something in free fall, except for, this sign is different. All right, I solve for V final. And again, here I get roughly 10 meters per second squared. plus 2 times g times 20. And wow, this term right here, due to the 20 meters of descent, gives me a really large term here. So I have like 10 here, and I have roughly 400 here. I'm pretty close to that, square root of 500. Take the square root, and I'm going 22.1 meters per second. Okay, not too bad on this roller coaster. I'm going roughly about 50 miles per hour at the bottom. That doesn't sound too bad until I calculate my forces. Here's where the problem comes. And I'm going to calculate my force in G's, mass times acceleration of gravity. Go back to our centripetal force equation. Now, when I'm at the bottom of the track, it's a little bit different because my weight is pulling down, but because I'm going around curved motion, my total force is still pointing to the center of the rotation. So my normal force is going to be really, really large, okay? Again, my weight is pulling down, my normal force is pushing up, but my total force has to point toward the center of the rotation, regardless of what other forces are present. So here, the normal force contributes to the centripetal force, pointing to the center, but the weight is in the opposite direction of that centripetal direction, center-seeking direction. So I get that my total force is equal to ma. I'm still going around a turn with a radius of r, that's 10 meters. I'm going at a much higher speed, so this term becomes squared. That's equal to this, and I'm going to solve for n. I move this to the other side of the equation, so it becomes plus mg. So n equals mg plus this term right here. Let me keep everything in terms of g's, okay? You'll see why in a second. So n is equal to m times g. So I have g plus this term right here. This is going to be my additional acceleration here. So my normal force is going to be 1g plus an additional, okay, almost 5 g's. My normal force, the force that I actually feel, the force that the roller coaster is going to push on me is going to be, because 1g is roughly 10 meters per second squared, it's going to be 6 g's. So, okay, 6 g's, just to give you some perspective, would cause most people to pass out, okay? At 6 g's, you also might have neck injuries from this. There's no way we want people to become injured on these rides or people to pass out. Okay. Yeah, people will pass out due to, I don't know, fear. But mechanically, we don't want the blood to be pushed out of their heads. We talked about this when we talked about centripetal acceleration and fighter pilots doing high G turns. So to correct for this, we don't make it completely circular. We make it more curved at the top to enhance that force from gravity, okay? So we can actually go a slower speed, all right? And then we flatten out the curve at the bottom so the centripetal acceleration isn't as great. We call this a clothoid, and it's the reason, it's roller coaster physics, why we have these roller coasters shaped the way that they are. And if you ride these roller coasters, you'll still experience quite a few G's at the bottom of the loop. But by expanding the radius of curvature, much larger than the actual loop itself, we can say maybe if we can make the radius of curvature 3 times larger, we can experience a more, a tamer, acceleration of maybe 2.7 Gs at the bottom. And still, that's quite a bit.